For my project, I wrote a simulation of a lattice gas using cellular automata. I implemented the FHP model, which is based around a hexagonal grid. The way it works is you have a lattice of points, each with 6 lines entering it. Particles travel with constant speed along these lines. You can have up to 6 particles at each point, one for each different velocity, as well as a stationary particle at that point. In this diagram, these stationary particles are indicated by circles around the point. The simulation is processed in 2 steps. First, the positions are updated as we move the particles along the grid. Then, at each point, we process any collisions and update the velocities of the particles. Here's an example of a head-on collision of 2 particles. Since there are 2 possible ways the particles could scatter while conserving momentum, we pick one of the 2 at random. This is an example of a 3-particle collision, and this is a chart of several different possible collisions, but not all. Any collision that conserves momentum and the number of particles is allowed. Here's an example of the simulation running at 50 by 20 sites. The red lines indicate the boundary, and we're using the no-slip condition, which means if a particle hits the wall, it's rebounded back in the direction it came from. I've made the brightness of each site be proportional to the number of particles there, so we can see them light up when particles collide. At large scales, it can be shown that the simulation follows Navier-Stokes equations, but at the small scale it's really hard to see what's going on. So let's skip to a bigger example. This simulation was run at about 1200 by 300 sites for 4000 time steps. Since everything's calculated locally in the simulation, it's really easy to have a large number of particles. Here we've got about 200,000. You can see that at the start of the simulation, it's quite unphysical, and we can clearly see the hexagonal structure of the grid coming into the motion of the particles. But as it progresses, it reaches an equilibrium state, where we have constant flow, and we start to see some interesting dynamics. On the right side of the wall, you can see 2 dark circles that correspond to vortices, but they're quite hard to make out in this picture, so we'll have a look at some other diagrams. This is an intensity graph of the average magnitude of the average velocity at each site. This is different than the average velocity of the particles, since we can have up to 7 particles at a site, 1 in each direction and 1 stationary. This means that lighter areas on the graph correspond to groups of particles all moving in the same direction. We can now see that it's a lot easier to make out the vortices on the right side of the wall. If we have a look at a flow diagram, we can see the direction of the particles as they move through the vortices. You can see that it appears physical, since everything flows continuously from one spot to another. Let's now have a look at a real-time flow diagram of a much larger simulation of about 2000 by 600 sites. In this simulation, as in the last one, we have periodic boundary conditions on the sides of the container. This means the particles flowing off the right side of the screen come back in at the left. We can now see how the flow of the fluid changes as we progress towards the equilibrium state. We can very clearly see the formation of several vortices in the flow diagram. And with more particles, we can actually see the changes in density in these vortices on the top graph as well. Here's an example of fluid passing around a circular obstacle, but in this case we don't have periodic boundary conditions. Instead, fluid is flowing in from the left at a constant rate, and when it reaches the right, it is removed from the simulation. We see in this case we get a constant shadow behind the object. We are also now getting laminar flow, and there are no visible vortices on the graph. Here we have a larger cylinder, and we see that we start getting some interesting vortices in the top left and bottom left of the screen, which we can see more clearly on the flow diagram. We also get vortices in the trail of the object when we get fluid moving back towards the cylinder itself. This is an example where we've increased the viscosity of the system. Not all of the collision rules are necessary in order to run the simulation. We can remove some of them, and doing so increases the viscosity. You can see that the motion of the fluid isn't as fine, and we get some interesting variation vertically along the channel. If you want to have a look at these simulations yourself, I've included the source code for the project, as well as some compiled simulations. All of the graphs and simulations were programmed from scratch using native Java, without using any external libraries.